Okay, guys, so in this video, we're going to talk about areas between the curves. This is 6.1. Now, when we say area between the curves, we've already learned in Calc 1 that the area under the curve, so that is to say the area between the curve and the x-axis, has a lot of similarities to the definite integral. So if we had something like this area, right? We could describe as the definite integral from a to b, since it's all greater than our x-axis here. And so that is when they are the same, but sometimes, well, many times, our integral, our definite integral, and areas are not necessarily the same. So if we had something like this, okay, if we took the integral from a to b here, this portion would be like a positive area, and this would be a negative. And so the definite integral takes positives and negatives into account to kind of get a net change, while area is strictly positive concepts. So there are similarities, but they're not exactly the same. Now, the idea behind these in general was that we're essentially taking little slices, like a line, one slice, and we're doing this infinitely many times throughout this and kind of adding them together. So these are just sums of a whole bunch of slices. Okay, think back to our approximations where we were doing little rectangles. Here we're doing just lines that have individually no area to them, but if you add a bunch of them together, infinitely many of them together, we actually get an exact area. So that's what we're going to be doing today. The only difference is now we're going to be talking about area between the curves. So we often think about this like area between a curve and the x-axis, but that's not the only thing we can do. We can also find the area between two curves. So that is to say, if we had something like here's one curve and here is another, and we wanted to find this area here, we can do that. Okay, now one of the things to note is that we often say curves and not like functions, and the reason why is because we're actually not restricted to just functions. What we're going to do is we're going to be able to take like non-functions like this and find their area as well. So we're not restricted to simply functions. We can do pretty much any curve. Now, the benefit of this is that we can talk about areas of much more complicated shapes than we would otherwise with, like, say, geometry. Because at the end of the day, when it comes to geometry, if we were going to try and describe complex shapes, even something like this, which is fairly complicated, can be kind of described in terms of like half circle, triangle, rectangles, etc. Okay, so essentially, we're not restricted to that anymore with calculus. We're able to use integrals to find areas of very complicated shapes that we wouldn't be otherwise able to do with geometry. Okay, now let's talk about the idea here. Just like when it comes to the kind of area under the curve that we know, where we take a bunch of slices, we're going to do the same thing when we have two curves here. So we have some bounded area here between a and b and our two functions. Now, sometimes we might just be interested at like their intersection. So if this kind of intersected here, we don't need to put boundaries. We would just say the area between the two curves because they form this area, but we can also restrict them as well. Um, so the idea here is that essentially we're going to take the height of each of these lines at each of these points, right? So if you think about this measurement here, it's increasing right now. So we're getting bigger and bigger, and then the lines are gonna kind of max out around here, and then they'll start shrinking again. But the idea is we're taking a whole bunch of these measurements here, and we are gonna add them together infinitely many times and get some area. So what we're trying to do is describe, well, what is the length of this distance here between these 2 points? Well, the length between them is simply the distance between them, which is the difference. If you take the high function here, the upper function, and you subtract the lower function, at any point you'll get that distance covered. For example, let's say that this point here is, I don't know, 1, 2. So this is the point here. And at the same time, this is like 1, negative 1. So if we think about that, the distance between these 2 points is 2 minus negative 1, which is 3. So the distance here would be 3, and that makes sense, 1, 2, 3. Okay, and we're going to do that over and over again. So what we do is we write, all right, well, our upper function f of x minus our lower function g of x, the integral from a to b. So we're doing this from a to b for every point on this line, essentially, and we're adding them up. Again, the integral is a sum. We're summing this infinitely many times. So the big thing to keep in mind is that we are always taking the upper function. The upper function is the function above. So here in our kind of definition, f of x has to be greater than or equal to g of x for all x in our interval that we care about. So if you notice over here, f of x goes below g of x, but that's okay because we're not interested in this region. But if we were interested in, let's say, this region as well, then suddenly all we have to do is break it up. This point here, the red is above, but then going forward, the blue is above. So we just think about it in that case, where we treated the blue one now on top. So it's just kind of like a sum of the two. Anyway, let's take a look at it. Determine the area between these two curves. All right, let's take a look at Desmos real quick so we can see it. When we're dealing with areas, it is really helpful to graph it because then we get an idea of what it is we're dealing with. Y equals x is this one. All right, so notice we don't have a restriction from A to B. We are restricted by the graph themselves. So if we look at this thing, we have this and here, okay? So the values here on the x-axis are from 0 to 2. Okay, this is where we're looking. So we have an integral from 0 to 2, and it's on the x-axis, so we call it dx. Okay, so let me actually snip this so I don't have to keep going back and forth. All right. So notice also the red function here is y equals 3x minus x squared, and our blue function here is y equals x. Okay. Let me shrink this down. All right, so we're dealing with this thing, and we want to find the area between these two curves. So we want to find this region. So what we want to do is we want to take the integral from our, we're doing it with relation to x, so from 0 to 2 on the x-axis, so dx. So we want to write our functions in terms of x's. So we are going to take our upper function minus our lower function. So that is this one, the red one, minus the blue one in terms of x's. So that would be 3x minus x squared. That's our upper function minus our lower function x. And again, we know we're using the x's because we're dealing with this in respect to x. So, and we're integrating from 0 to 2 on the x-axis. So all those things help us know which to use. So 3x minus x is going to be, this is the integral from 0 to 2 of 2x minus x squared dx. Okay, so this will find the area between these two curves. So we will integrate it. This would be 2x squared over 2 minus x cubed over 3. And we're going to integrate it from 2 to 0. Or, well, 0 to 2, but anyway. So 2 squared is 4. These 2's cancel. We just have 4. Minus 2 times 2 is 4 times 2 is 8. 8/3. And then it's minus plug 0 in. Well, that's just going to be 0. Okay. So if we think about this, if this is 3, this needs to be multiplied by 3 as well, so that would be 12. So 12 minus 8 is 4/3. And this is the area between these two curves here. Now, we don't have to worry about like whether this curve is below the x-axis or above it. This area will work itself out. All that matters is that the upper function is always the upper function during the region we're integrating. So in this case here, we're integrating from 0 to 2. So from 0 to 2, f of x, or excuse me, our red x, 3x minus x squared, our red function here, this is greater than our blue function during that time. So we're okay here. All right, let's do another one. Determine the area between these two curves. So we have another y equals x, nice simple graph there, and we have x minus 2 squared. Okay, so again, we have another region. This region now is from 1 to 4. We're integrating from 1 to 4. And again, it's going to be our upper function. We can think about this as like upper function minus lower function if we want. And we have dx here. So let's take a look at our upper function during this region. It is our y equals x. And our lower function is our x minus 2 squared. So we are going to take our integral from 1 to 4 of our upper function, x, minus our lower function, x minus 2 squared, dx. And again, we're doing dx because it's from 1 to 4 on the x-axis, and so we're writing this in terms of x. Also, our upper function is above it, and this is the lower function below it. We'll talk about doing it with respect to y in a bit, but for the time being, this is good. Okay, so in order to integrate this, we're going to have to FOIL this out. So this is the integral from 1 to 4 of x minus x squared minus 4x plus 4 dx. And so we are going to distribute this negative throughout. Integral from 1 to 4 of, so x plus 4x is going to be 5x minus x squared minus 4 dx. And we are going to integrate this. This would be 5x squared over 2 minus x cubed over 3 minus 4x. And again, I don't do plus c's in general when we're doing a bunch of definite integrals because we don't need them in our definite integrals. But as they cancel out, just as a reminder. But if you are worried that maybe you'll forget to say plus c on other integrals, then it might be worthwhile to say plus c on them. You'll just see I don't do that if I'm doing a lot of definite integrals. If I'm doing like a one-off definite integral and otherwise doing a bunch of indefinite integration, then I do just do the plus c just to make sure I'm in the habit of saying plus c. Anyway, so if we put this 4 in, we have 5 halves times 16 minus 4 cubed, whatever that is, over 3 minus 16 plus c, and then we say minus, plugging 1 in, we have 5 halves minus 1/3 minus 4 plus c. Now, the reason why we, as a reminder, do not need to write the plus c in definite integration is because plus c minus c cancels. So these two are gone. We're distributing this negative into each of them. Okay, so I'm going to just go over to Desmos and type this in so I don't mess something up. We have 5 times 8 minus 4 to the third over 3 minus 16. Then we have minus parentheses 5 halves minus 1/3 minus 1/3 minus 4. Okay, and we get 4.5, which is 9 halves. And that is the area between our two curves, this region right here. Okay, let's do another one. Determine the area between these curves. We have the area between secant squared x, 8 cosine x, and it's on this interval here. So now we have some interval restriction. Okay, so if you want to do interval restrictions on Desmos, we can do that. I'll do that in a sec. Let's just write this. F of x is secant squared x, and g of x is 8 cosine x. Now the benefit, so if you look here, first of all, there's a lot of regions that we're interested in, but more specifically, we're interested from negative pi thirds to pi thirds. So it's this region here. And if you struggle to find it, it is worthwhile to do piecewise functions on this. So if we're going to restrict the domain, what we do for a function is we name it f of x or g of x, it doesn't matter, and we say equals, and then we say squiggly bracket, and we define the domain. So this is negative pi over 3 is less than or equal to x, which is less than or equal to pi over 3. Then we say colon. So if you notice, we have restricted that. Now we're going to do the same thing here. I'm just going to copy it so as to not have to waste a bunch of, maybe I'm not going to copy it. Yeah, there we go. So I'm going to say equals squiggly bracket, same domain restriction here. So we're looking at this region here. And again, we have our upper function and our lower function, and that's important to know which one's which. Okay, otherwise, essentially, in general, if you do the wrong way, it will kind of give you like a negative of it, which, I mean, as long as you recognize it's a negative of it, it's not really a big deal. You just always, our areas are always positive, so it wouldn't necessarily break it, but, you know, it's still worth making sure we have it the correct order. So the black one here, 8 cosine x, is the upper. So this is 8 cosine x. And the lower, the purple one here, is our secant squared x. Okay, so we are going to take our upper minus our lower. So this is the integral from negative pi thirds to pi thirds of our upper function, 8 cosine x minus secant squared x dx. Okay, so the integral of cosine is going to be sine, so this will be 8 sine x minus tangent x, derivative of tangent is secant squared. We're taking this from pi thirds to negative pi thirds. Okay, so this is a special angle, pi thirds. So trig cheat sheet. Just to remind you, we have our unit circle, pi thirds, pi fourths, pi sixths. These are all like our kind of special angles. Anytime we see one of these things, we need to make sure that we are being exact. Okay, so sine of pi thirds. Sine of pi thirds, it's always cosine then sine. That's square root 3 over 2. So we have 8 times the square root of 3 over 2 minus tangent of x. Now, as a reminder, tangent is sine over cosine. I should write tangent x because tangent doesn't exist on its own. It needs an x or something. But that's sine x over cosine x. So we can still use the unit circle here. So tangent would be sine over cosine. So that's square root 3 over 2 over 1/2. Now, that's the same thing as saying times 2 over 1. So we'll go ahead and just write that. Times 2 over 1. And if you notice, that's just going to be a negative square root 3. So that's nice. Minus, okay, now we're going to do our negative pi thirds. So negative pi thirds would be 300 degrees or 5 pi thirds, however you want to think about it, but it's negative 60 degrees here. So it's going to be a negative square root 3 over 2. So 8 times negative square root 3 over 2 is our sine, minus our tangent is also a negative square root 3 over 2 over 1/2, just like this. So times 2 over 1, like that. Okay, so this becomes a positive. The 2's cancel. Clean this up a bit. 8 and 2 makes 4 square roots 3 minus square root 3 minus a negative. So this is also a 4 and this becomes 1. So that's a plus 4 square root 3. And then we have minus square root 3. Okay, these are all like terms, so we can combine them. 4 plus 4 is 8, minus 1 is 7, minus 1 is 6. So that's 6 square roots 3. And that would be our area. Okay, so that's when we have like a single region we're worrying about. Now let's take a look at this. So say we have this function, y equals x cubed minus 3x. And we want to find the area here. Now, first of all, if we notice, this is from -2 to 2, okay? And this region here, our blue function is above, but then this region here, our red function is above. So what we need to do with something like this is we need to, that's not what I wanted. We need to break it up into two integrals, okay? Because if we just were to integrate from -2 to 2, treating this one as the upper, well, we'd end up with a 0 because it would be positive here and negative here. And we want to know like the area. So this is a negative region, this is a positive region, and I'm expecting them to be the same because this has like a symmetry to it. So I'm expecting the two to be the same. We'll see that in a bit. And so if I just were to integrate either one of these from -2 to 2, treating either the red on top or the blue on top for both, it would end up with a 0. So what we need to do is we need to split it up into two integrals. The integral from -2 until x is 0, dx, and in that case we're doing the upper function, so that is x cubed minus 3x minus the lower function, which would just be x. Okay, then we're going to add that to the integral where the red function is bigger, so that's from 0 to 2, and that would be x, minus our lower function, which would be our x cubed minus 3x dx. Okay, so I should have parentheses technically around all of them, but whatever, it doesn't matter. Like this, since the dx is with everything, but I'm often lazy. Okay. The integral from -2 to 0 of x cubed minus 4x dx plus the integral from 0 to 2 of x plus 4x is going to be 5x minus x cubed dx. Okay, so by splitting this up, this is a 0. My handwriting's a little bad sometimes. I know it's a 0, but you might think it's a 6. Okay. So we need to integrate this. This would be x to the 4th over 4 minus 4x squared over 2 from 0 to -2 here. Plus, we have 5x squared over 2 minus x to the 4th over 4 from 2 to 0. Okay, so plugging in 0 here, we get a 0, nice and simple, minus -2 into this, that's to be a positive, 2 times 2 is 4, times 2 is 8, times 2 is 16, so that'd be a positive 16 over 4, minus a positive, so this is just 2 here, so minus a positive 4 times 2 is 8. All right, plus, now over here, plugging in 2, we have 4 divided by 2 is 2 times 5 is 10 minus 2 times 2 is 4 times 2 is 8 times 2 is 16 over 4. Okay, so that's that one, minus plugging in 0, that's just a 0 there. Okay, so negative, this would be 4 minus 8 plus 10 minus 4. So 4 minus 8 is negative 4 minus, so that's a negative of a negative, it's positive 4. And then 10 minus 4 here is going to be our 6. Okay, so something's up here. 16, let's double check this math here. 5 times 4 is 20 over 2, that's 10. Okay, let's check this math then. Negative 2, I'm just expecting the areas to be the same, if that makes sense. So that's why I'm just double checking my math here. Minus 4x, we have 5, oh, that's why, huh? I don't know how I added this wrong. Okay, so sorry about that. But again, I was expecting it to be the same. So when I saw that this was 10, minus 4 being 6, and this was 4, I knew something was up. So everything here is okay. Let's just check, let's just correct this. So this would be a 4x squared over 2. So the only thing that changes here is that this would be 2 times 2 is 4, times 4 is 16, over 2, that's going to be 8. Ah, that's a lot better. Okay. You're probably sitting there screaming at your screen anyway while I screwed that one up. That's why I don't do math in my head, because I can't even do arithmetic. All right, so we have this plus 4, and then we're going to have a plus 4 here. So we get a total of 8. And again, we expected them to be the same, so that's how I knew that something was up. Because again, there looks like there's symmetry here. So it seemed unlikely for these two to be different, unless I'm just not able to see like a slight difference in their functions or something like that. Anyway, so that is our area with respect to x. Now, sometimes we end up with things, oftentimes they're non-functions. So if you look here, this like blue and this red are not functions, but there's some curve. And so occasionally it's actually a lot harder to integrate this thing with respect to x to find its area. So instead, we just do it with respect to y. And it's really just a matter of which one's going to be easier. So if we have some region bound by the curves x equals f of y and x equals g of y, and y is between c to d here, and we know that f of y here, the red function, is always going to be greater than or equal to g of y here, the left function. So in this case, notice the quote upper function is actually the right function and the lower function is the left function. Then we can find the area by taking the integral from c to d of our right function minus our left. And this actually is a lot easier to describe in those terms. So rather than thinking about it as like uppers and lowers here, we're thinking our right function and our left function. And notice we're integrating with respect to y. So we need to write these two equations, right and left, in terms of y as well. So this is how I think about it rather than in terms of like, you know, g of y and f of y or whatever. So let's see this in action. So in this case, we have these two equations. Neither of them are functions, but like which one is above and which one's below? Well, that's a problem of why we're not going to use x to deal with this, is because to find this thing here, you know, we'd have to take from x to x, and so we'd have to find where these things are. Not necessarily a challenge on like Desmos. So here we have x equals y squared minus 4y. I'm doing it all in caps on accident. X equals y squared minus 4y. We have x equals 2y minus y squared. Okay. So we have this thing, and again, we could certainly find where, you know, if we wanted to integrate this with respect to x, then we'd have to do something like from -4 to 1. But the problem here as well is that like, in order to like integrate this with respect to x, we have to get this in terms of y equals some function of x. But this is a y squared minus 4y. There's no easy way here to solve for just y, to isolate our y, because we have y's of different like values here. Same thing over here. We don't have an easy way to solve for y, to get y by itself. And so that is our problem here. So instead of trying to work with some implicit equation here and try and force it into an explicit terms, which may or may not even be possible, we just give up on that x-axis and we just worry about the y-axis then. So now we're going to go, all right, well, we're going to integrate from here to here on the y. So that is from 0 to 3. So we will integrate from 0 to 3 on our y-axis. So we're going to do this as a dy. And our upper function is in terms of y to the right. This is our lower function to the left. Okay, so we have our upper function, that is our 2y minus y squared, minus our lower function, y squared minus 4y. Okay, so doing a little bit of cleanup work here, the integral from 0 to 3. So 2y plus 4y is 6y. Negative y squared minus y squared is minus 2y squared dy. Now, when we integrate with respect to y, these y variables are just treated like our variables, like they should be. So, we generally do things with respect to x, but we can integrate with respect to any value we want. It doesn't really matter. Okay, it's just those become our variables. So we need this in terms of y to be able to do that though. So that's why we have them in terms of y for our dy. So this is 6y squared over 2 minus 2y cubed over 3. And we are integrating from 3 to 0. So 3 squared is 9. This is just a 3. So 3 squared is 9 times 3 is 27. Minus 3 cubed over 3 is going to be a 3 squared, so 9 times 2 is going to be 18. And we get 9. And 0 into this is just 0, so we're good there. And we get our area here is 9. Okay, so again, nothing special about this. The only difference is we change what we're integrating with respect to, and then whatever we're integrating with respect to, that's our bounds of integration, is in terms of y as well. So from 0 to 3 here, from 0 to 3. Okay. Anyway, so let's do another one. Determine the area between the curves. Okay, so in this case, again, we are not solved for y. We're solved for x. So if that's the case, then it's just going to be easier to describe this in terms of y than x. So there's no reason to force it. So just looking at this and seeing that x has been solved for but not y, then I know that I'm probably going to integrate this with respect to y. But let's take a look at the graph to just make sure that that's going to be the easiest route, because we could certainly solve for y for both of these, move the 1 over and take the square root, and we'd have a plus or minus though. So that would be, maybe problematic, but x equals 1 minus y squared, okay? And x equals y squared minus 1, okay? All right, so as mentioned, is like if we solve for y here, that's not like it's not doable. We just it's going to make it worse for us. So like solving for y here, we'd move the y squared over, subtract the 1, or subtract the x. We'd have y squared equals 1 minus x, take the square root, we get y equals plus or minus the square root of 1 minus x. And then over here, same thing, add the 1, square root it. We'd have x plus 1 square root plus or minus is equal to our y. So let's just take a look at that. So if we want to think about it in terms of x, that's doable. But let's take a look first on this green one. The square root of 1 minus x is this upper side here. And so the negative of it would be the lower. And so essentially you'd have to break this singular equation up into two things. And we do the same thing over here, square root x plus 1 for the upper, and negative square root x plus 1 for the lower. So if we were doing this with respect to x, we'd basically have to integrate from -1 to like 0 here and find this region with respect to the x-axis, and then we'd have to integrate this one from -1 to 0 to find this one here, and then same thing here and here. So we'd basically have to do it in like 4 groups potentially. We could also maybe do it where this is the upper function and this is the lower function, integrated from -1 to 0. That would also work, and so on and so forth. But again, that's adding challenges to this when there's no real need to. It's not that you can't, it's just that why bother when this is easier to deal with. Okay, so let's go ahead and take a snip of this so we have it. Because again, I like to, even though I'm expecting to integrate it with respect to y, I'm still going to double check. And I'm going to graph these because it's just so much easier to think about this area when I have a picture of it. So our upper function is this one here, which is the green function. Okay, that's this one here. So that is 1 minus y squared minus the purple function, which is this one here, y squared minus 1. And again, being careful with the parentheses here because that negative distributes. And again, we're doing it with respect to y, so that's why I'm writing it in terms of y. And so our bounds of integration are from -1 to +1. Okay, now we have this thing, integral from -1 to 1 of 1 plus 1 is 2, negative minus a negative, that's gonna, or minus positive here, that's gonna be negative y squared, this 2y squared. Okay, dy. Okay, so integrating this thing, we have 2y minus 2y cubed over 3 from 1 to -1. All right, so plugging 1 in, we have 2 minus 2/3 minus -1, that would be a -2. That's going to be a negative, and a negative makes a positive 2/3. Okay, so 2 plus 2 is 4. Negative and a negative makes -4/3. So if this was over 3, then this would be multiplied by 3, so that's 12. So 12 minus 4, that's 8/3. Okay, so that's our area of this region. All right, let's do another one. Okay, find the area of the region enclosed by the curves using both x's and y's as a variable of integration. So essentially, in something like this, let me take a look at kind of explaining this as something that we can do in both x's and y's, because again, they should be the same regardless. I mentioned that in the previous one, but let's actually see that in action. Okay, so I had to plug in my headphones there. So we have y equals 1 over x. Let's go ahead and graph this so we can get an idea of what we're looking at. Y equals 1 over x. We have y equals x and y equals x over 4. Okay. So we want to find some region bound by this thing. Okay, now let's actually give the graph some boundaries here, because if you look here, like we actually have a few regions that you could maybe call bound, this region and this region, but I'm strictly talking about this region here from this point to this point. So this region here. Okay, let's go ahead and find these corner points. Now, if we didn't have Desmos to find these corner points, as a reminder, how do you find them? You set the functions equal to each other to solve for their intersections. Okay, I just use Desmos because this isn't algebra anymore. I don't really care about doing that all by hand here. Okay, so let's go ahead and plug this in. Okay. Let's talk about it in terms of x first. So if we're talking in terms of x, now that means we're going to integrate from 0 to 2 overall. But we notice that from 0 to 1, the black line here is the upper function. And then from 1 to 2, the purple line is the upper function. So we're going to have to split these up into two things if we're doing it by x. Okay, so here, if you notice, essentially we're going to take this region and this region separately. Okay, real quick, this is y equals x graph here. This is the purple one, just to double check. I believe it's x over 4, but let's just make sure. Nope, it's 1 over x. Good thing I checked, huh? 1 over x. And the red one here is, so I should say that this is y equals, and the red one here is y equals x over 4. Now, because all of these are already solved for y, I would actually lean towards solving it in terms of x, just because that's probably going to be easier for me. But we could certainly do it in terms of y as well, which we'll do in a bit. So, but let's first think about it in terms of this thing here. Again, we are taking a look at the left integral and then the right area kind of here. So we are going to integrate from 0 until 1, the black function, that is x, minus the red function, x over 4, dx. Okay. Again, we're doing it in terms of x's, so we need our function in terms of x's. Okay, this is going to be x squared over 2 minus, well, the reality is I'm not going to integrate this yet. Let's just simplify this. That would be a 4x over 4. Then this is the integral from 0 to 1 of 3x over 4. Okay, so this is our like left-hand portion that we're going to be integrating. Let's talk about the right-hand side though while we're at it. This will be added to the integral from 1 to 2 of now the upper function, which is 1 over x, minus the lower function, which is x over 4. Okay, so let's kind of clean this up a little bit. Well, it's not going to be cleaned up, so whatever. Plus the integral from 1 to 2 of, well, I'll rewrite this. This is x to the negative 1 minus x over 4 dx. But this is a 1 over x or an x to the negative 1. I didn't really have to do this because we're not going to use the power rule. We're going to use our log. So the integral of 3/4 x is going to be 3/4 x squared over 2 from 1 to 0. And over here, we're going to add that to natural log of x minus x squared over 4 times 2 here. Okay. And we're going to do that from 2 to 1. Okay, so if we plug 1 in here, okay, we end up with, well, first of all, this would be 3/8 times 1, it's just 3/8 minus 0, plus natural log of 2 minus 2 squared is 4 over 4, that's just going to give us our 1/2 here, okay, minus 1, natural log of 1 is 0, minus 1/8. Okay, so cleaning this up a little bit, 3/8 minus 1/2 plus, so that's an 8, natural log of 2 minus 1/2 plus 1/8. That's going to give us 1/8 plus 3/8 is 4/8, also known as 1/2 minus 1/2 plus natural log of 2, natural log of 2. Okay, so we found this region here. The sum of this is the natural log of 2. Okay, now we should see if this checks out for this in terms of y. So I'm going to copy this. I'm going to create a new slide and bring it over. Okay, again, this is our y equals 1 over x. Okay, this is our y equals x. And we had x over 4. Now, if we do it in terms of y, we have to break this up here, okay? Because what's the right-hand function? This is the right-hand function from 0 until 2. But then the right-hand function is purple function here from from 0 to 1/2, and then from 1/2 to 1, okay? So we're going to find this region, this lower region, and the upper region, and we're going to add them together here and here. But if we're going to integrate with respect to y, that is, we're going to take the integral from 0 to 1/2 of the red function minus the black function. But we're going to do it with respect to y. We need these in terms of y, not in terms of x. Now the black function's already in terms of y, so that's easy enough. But let's solve for x here. Multiply by 4. That would be x equals 4y. Okay, over here, if we're going to solve for x, multiply the x, divide the y, we get x equals 1 over y is this purple function. Okay, so again, we want it in terms of y here. So first region, from 0 to 1/2, it's the right hand. So that is 4y minus the left hand, y. Then we're going to add this to the integral from 1/2 to 1 of our purple function now. So that is 1 over y minus y dy. Okay, so let's go ahead and try this out. So this is 4y minus y. That's going to be a 3y that we're integrating from 0 to 1/2 dy. Plus, we could certainly do this one if we wanted, but then that would turn it into a rational, so it's actually better in this form than combining them. So it's the integral of from 1 to 1/2 of our 1 over y minus y dy. Again, because it's 1 over y, that's natural log, so we're okay there. Oh, I should note on this previous one, when I did natural log, it should have been of absolute value, but because we're positive, I didn't mention that. This is only positives anyway from 1 to 2, so I didn't have to do an absolute value. And the same thing's going to apply here. Like when I do that, it's from 1/2 to 1. That's strictly positive anyway, so it doesn't matter. We don't need the absolute value symbol. Okay, so this would be 3y squared over 2 from 1/2 to 0 plus natural log of y, again, don't need the absolute value, minus y squared over 2 from 1 to 1/2. Okay, so plugging this thing in. So 1/2 squared is 1/4, so that's 3/2, so 1/4 here. Okay, minus 0 plus natural log of 1 is going to be 1 here. Okay, excuse me, natural log of 1. 0 minus 1/2. Okay, minus natural log of 1/2 minus natural log, or excuse me, minus 1/2 squared, that'd be 1/4 over 2. Okay, terrible 2. Let's try that again. Okay. So, trying this thing out here, we have this thing natural log of 1/2. Now, let's take a look at that really quick. Okay. Now, in this case, if you see natural log of 1/2 is strictly positive, that's fine. But why is this going to be like a natural log here of 1/2? Why is this a negative of natural log of 2? Okay. Well, essentially, the reasoning for this is that if we think about this, this is like saying, well, we'll clean it up first. We'll deal with it in a sec. Okay. So 3/4 over 2 is like saying times 1/2. So that would be 3/8. Okay, minus 1/2 minus natural log of 1/2 plus 1/8. So we get 4/8 minus 1/2 minus natural log of 1/2. So this cancels, 1/2 minus 1/2. We have negative natural log of 1/2. Okay, now, if you think about this, let's write this in terms of like 2 to the power. So this is negative natural log of 2 to the negative 1. That's what this actually is, okay? It's 2 to the negative 1. This is the same thing. Now, we know from our log rules that when we have some exponent, so we have log of something to a power, we can bring that power down in front of the log. In fact, that's usually how we use our logs, is solving like exponentials to get x out of the exponent. So this negative and this negative makes a positive natural log of 2, which is the same value as we got on our previous one. Okay, so that is our like 2 of these. Like again, in something like this, it's just a matter of choosing what's easiest. So we had to separate it into 2 regardless, so there wasn't really an easier way. The only thing I would note is that in terms of x was maybe easier because we already solved for y in those functions. We didn't have to solve for x to get to it. Additionally, we don't have to worry about some log rules here that are maybe problematic for some students. But the end result is it doesn't matter whether we choose it in relation to x or y, we just always pick the easiest. Sometimes there is no easiest, both of them are not great, but oftentimes one is better than the other. And so we just choose what we integrate with respect to for those. So whether it's x or y, all that matters is that we choose our variables appropriately. So that is our area. The goal of this is to find areas, but eventually we're going to move, in fact, the next section, we're going to talk about volumes, which follows similar concepts. Okay, so thanks for watching.